Okay, we're going to finish up with this. This won't take super long, and then I'll let you guys go. But we're going to make some stuff erupt finally. We'll take all the physics that you've learned and try to put it together. So let's draw a picture here. So let me draw this out here. So here's the surface, and let's say we have a magma body right here. Is that magma body under pressure? What's the pressure from? Yeah, so it's the lithostatic. It's got rock above it, right? So there is some pressure, L, lithostatic, pushing down on your magma body, right? Now, if it's in equilibrium, the pressure in the magma is going to be doing what? Pushing back up at the same amount, right? If that's the case, is the magma going to move? No, so you need more magma pressure than lithostatic pressure, right? So let's say you had more magmastatic pressure than lithostatic. Does that mean it's automatically going to move? This is solid rock, right? Solid rock sitting above it. In order for it to move, it needs a pathway, right? It needs to find an opening to flow through. It's liquid. So in order for it to actually move, the magma pressure doesn't only need to exceed the lithostatic pressure, it needs to break a path. In order to break a path, it has to exceed the rock strength as well. So once you exceed the rock strength, then that magma can move to the surface. So in order to get an eruption, your magma pressure has to be greater than the lithostatic pressure and the strength of the rock. It has to be enough to move up, but it also has to have enough pressure to break the rock. What if the rock's already broken? Then it's easier for it to move, isn't it? So we're going to use this little equation to figure out how to make a volcano erupt. So down below, we've got some magma. It's got magma pressure. Depending on the depth, it's going to be crushed by lithostatic pressure. And that rock sitting above the magma body's got some strength to it. The stronger the rock, the harder it is to erupt it, isn't it? You need more magma pressure to break a strong rock than a weak rock. So let's start with the condition that magmastatic pressure is less than the lithostatic plus the rock strength. If that's the case, is it going to erupt? No. So this is like 90% of the magma that's in the earth. It doesn't have enough pressure to overcome the lithostatic and the rock strength. So it just sits down there. Okay, so look at that equation. It's just pretty simple math. How do we get this stuff to erupt? What can we change? What's the most obvious thing to change, do you think?
The right side of the equation.
Okay, we could do what to the right side of the equation? We could lower the rock strength, right? We could lower the lithostatic, or we could increase the magmastatic pressure, right? So 3 things we can change. We can make the magma more pressurized. We can make the rock above it weaker. Or we can change the lithostatic pressure. All 3 of those can actually trigger volcanic eruptions. Let's take this first case, the magmatic pressure. Magmatic pressure, remember, comes from buoyancy, from a density difference. That's what's giving it the tendency to rise, right? It's less dense than its surroundings. Well, if we can make it even less dense than that, less dense than it is right now, that's going to give it more pressure to rise. How can we make the magma less dense? Well, one way would be to grow bubbles. Make more bubbles in there. That would make it more buoyant. How do we make this magma more buoyant? Well, there's really 3 different ways that volcanologists have thought of that could make this happen. The first one, diffusion, simply means that the bubbles grow slow as gases come out of solution and move into bubbles. What I have listed for B here is rise of deeper bubbles. So let's say you have lots of bubbles sort of evenly distributed in your magma. Over time, those bubbles are going to want to rise to the top of the magma chamber. Once they do that, that top of the magma chamber then is hogging all the bubbles, and it becomes very low in density, and that will increase the pressure to move it upward. It increases its buoyancy. Sometimes magmas can mix. You can have a volatile rich magma come in from somewhere else and inject some more volatiles into your magma chamber. That can increase the bubbles and make it rise. So in these 3 cases, we're trying to get the bubbles to grow, make the density of the lava less, and give it more pressure to rise upward. And there's a 4th way, and this is the way we think most eruptions go. This one's a little harder to follow, so you're going to have to sort of stay with me on this. So let's say we have magma. Here's a magma body. Let's say it has 4.9% volatiles. Now let's say the solubility of gases in your magma is 5%. What that means is that your magma can dissolve 5% gases in its liquid. Anything more than that, it's going to form bubbles. It's going to exceed the solubility, and those gases will come out of solution and form bubbles. Right now it's 4.9%. Will bubbles form in this case? Do you have enough gases to force bubble growth? The answer is no. If they can handle 5% and you're only at 4.9%, can't do that, right? So let's say this magma over here just sits and starts to cool off a little bit. What happens to magmas that start to cool? They start to crystallize. Let's say you start to make solid crystals that don't incorporate any gases. Okay, so now you've decreased the amount of melt here, haven't you? You've grown some solid crystals, so the amount of melt is less. But all the volatiles are still there. So what does that do to the percentage of volatiles in the melt? It raises the ratio. So now, rather than 4.9, you might have, let's say, 5.1. You haven't changed any of the volatiles, you've just lessened the amount of melt. Does that exceed the solubility? Will bubbles grow? Yeah, some of these gases will start forming bubbles. And as these crystals keep growing, the bubbles are going to keep growing. So it seems kind of odd, and I think this is the hardest thing that people who study volcanoes have to contend with, is that cooling a magma can actually make it erupt. You think, oh, you know, when things cool off, it's going to be somehow less prone to erupt. You know, you need heat, you need energy. As it turns out, by cooling it off, you form solids that increases the amount of volatiles in the remaining melt, driving up the concentration until you get bubble growth. This is believed to be the mechanism that made Mount St. Helens erupt, that makes dome eruptions common at volcanoes like St. Helens. So this is one I really want you to remember, is if you crystallize anhydrous minerals, anhydrous means they don't incorporate water. They leave the water behind in the melt. I mean, think of it this way. If you had a magma, let me get rid of all these crystals here. You had a magma that had 5% volatiles and no crystals, okay? The concentration of volatiles is 5%. What if you crystallized half of it? Make little crystals form here that don't incorporate any of the volatiles. And let's say you did that to 50%. That doubles your concentration, doesn't it? Because all those volatiles are staying in the remaining melt, which is now half the size. If you have the same volatiles in half the space, that doubles the concentration. So you drive up the concentration by forming crystals. And if you exceed the solubility, then those volatiles move out of solution into bubbles and create a buoyant force. So this is probably the main way that magmastatic pressure is increased. Okay, so if we don't increase the magmastatic pressure, what were our other options? We can lower lithostatic or lower the rock strength. How can you lower lithostatic? Remember, lithostatic has to do with the weight of the overlying material. Probably the easiest way to change the weight of the overlying material is to make it thinner. Because remember, lithostatic pressure equals the depth times the density times gravity. All right, we're not going to change gravity. It's also really hard to change the rock density. But we can change the thickness of the overburden. One way this probably happens easiest is by landslides, where you have a sudden release, a sudden lessening of the thickness of rock over the magma chamber. So that's a rapid way to change the overburden. One way to do it more slowly would be to slowly erode the volcano. If you want to do it really slow, you can use tectonics in extensional areas to thin out the crust, stretch the crust and thin the crust. It's also being suggested now that melting ice off a volcano could change the overburden weight. Or if you had oceans that were shallowing, that could change the weight over a submarine volcano. So in all cases, you simply want to change the overburden. You want to lessen the thickness of material above it. Extend and thin the crust, erode the crust, allow landslides off of volcanoes, or shallow oceans or ice caps. All right, what's left? We changed the magma pressure, we changed the lithostatic pressure. What's less? What's left? The rock strength. This one definitely happens also. Yeah, if you have magma that has excess pressure over lithostatic, but the rock is too strong, sometimes what can happen is that gases that are released from that magma slowly over time can sort of corrode or rot the overlying rock. You can form hydrothermal systems over magma chambers that make the rock super weak. And this probably goes back to something you learned in physical geology. There is a weathering process called hydrolysis. Hydrolysis is where you take a strong silicate mineral like a feldspar or an olivine. Do you guys remember the hardness of olivine, roughly, or the hardness of feldspars?
7 to 10.
They scratch glass, right? So they're up around 7. So these are tough minerals, right? When you subject these minerals to water, more specifically acids, what can happen is the hydrogens from the acid can knock out cations. So remember let's just take an olivine. An olivine is a tetrahedron with 2 irons. Iron plus 2, iron plus 2. That's an olivine, okay? Really strong bonds. This stuff is not easy to break. But what happens with hydrolysis is that if you have acidic waters, and acidic waters have excess hydrogen in them, that's what makes them acids. 2 of these hydrogens can come in if they hit with just the right velocity and the right angle, they can kick out that iron. And then 2 more hydrogens over here can come in and they can kick out that iron. When you do that, this material then turns to clay. You guys remember the hardness of clays? Not very strong, right? Hardness of 1 to 2. So what you do is if you have hot acidic waters, remember heat makes these reactions more energetic. Acids have lots of hydrogen. So if you have hot acids coming off of your volcanic magma chamber, which is something that happens a lot, it can actually take these hard silicate rocks and turn them to clay and greatly reduce their strength. So what can happen at volcanoes is that they can just sit there for the longest time. Nothing changes. Magma pressure doesn't change. Lithostatic pressure doesn't change. But if that material rots enough, it becomes weak, allows a path, and then that magma can rise through it and make its way to the surface. Sometimes also we can have cooling fractures that form in rock, and that provides pathways for the material to rise as well. So basically what I want you to remember are 3 ways to trigger an eruption. Increase the magma pressure by making more bubbles. Decrease the lithostatic pressure by thinning the overburden, or decreasing the rock strength, mainly through hydrolysis. So next class, we're actually going to talk about real eruptions. We'll spend the whole class period talking about how to classify eruptions. We'll talk about famous eruptions. We're going to get away from the physics and the chemistry for a while. Every once in a while, I'll refer back to yield strength and viscosity, but at least for the next month or two, you're not going to see as much of the physics as you have up to this point. So we'll transition into how volcanoes actually behave now. Do you guys have any questions?